Hello everyone. In this video, I am going to discuss how to design a rectangular single reinforced beam section. Here, these are the data we have. The concrete strength is 25 Newton per square millimeters, and the strength of the steel is 460 newtons per square millimeters, and the maximum bending moment it should be stand with the beam is 150 kilonewton meters. And this is about the section dimensions of the section. It's just like, as this one is rectangular, it's just like this, and the overall depth capital D is 50 millimeter larger than the effective depth. This is the effective depth. The difference between the total depth and the effective depth is 50 millimeters. Okay, this is a rectangular section, and first I assume that this section is at yield stage. So I take x over d is equal to 0.5. It means this is the neutral axis, depth of the neutral axis. This is the effective depth. The ratio between the neutral axis and the effective depth is 0.5. I take it as the assumption. So the neutral axis is like this, and the depth to the neutral axis is x. With the single reinforced section, if it is a singly reinforced section, according to the BS 8110 3.4.4.4 clause, we have to maintain the K value below the 0.156. Okay, this is under 3.4.4 is the clause in BS 8110. We are designing this one under BS 8110 code. Okay, there K value is equal to M over BD squared FCU. Here B means the breadth, this one is the width, and the D is here effective depth, and FCU means the strength of the concrete. Here, with my experience, I take the ratio between B over D as half. It means depth is twice from the width. It means width is half of the depth. Depth is here effective depth. Okay, so B equals 0.5 D. D means effective depth. Okay, here we know that M is equal to 150 kilonewtons meter, and B equals 0.5 D, and we don't know the D value here. FCU equals 25 newtons per square millimeters. So we can calculate the K value, that is 150 10 to the power 6 Newton millimeters, and for B I take this value d, and this is d squared, and this is 25. Okay, first we have to check with the k equals 0.156. This is the limitation, or this is the margin of k value to be a single reinforced section. By substituting this 156 into that equation, we can find the minimum depth or the minimum effective depth here. 150 into 10 to the power 6, 0.5 d cube 25. By substituting d, we can find d as 425 millimeters. By solving this equation using a calculator, we can take this value. The effective depth, which must be the minimum one. We can take any value greater than this d, and when d is greater, in this equation we can identify that this value, this k value becomes lower when this d increasing. So we can get any value greater than this one or equal to 425. Here I select d as 425. I am adding another 50 for my safety, so then it is 475 millimeters. Now the effective depth is 475. As there is a data d is equal to total depth minus 50, I can get the total depth as 475 plus 50. It means 525 millimeters. Okay, now we know the section sizes as d is equal 525. This is the total depth. Effective depth as 475, and at first we took that here width is equal to half of this one. It means here near 250 to 40, so I take it as 240 millimeters. Okay, now we know the section sizes, and we have to design the reinforced amount or the area of the reinforced to withstand the bending moment. New section sizes, we can check the k value. K is equal to m over bd squared fcu. This value must be now below the 0.156 value, so we can check it. 150 into 10 to the power 6, d is now 240, and d is now 475 squared 25. Now we can find the k value by using a calculator. That is 150 into 10 to the power 6 divide 240 into 475 squared into 25. Value is 0.1108. As this one is below the 156 value, so this can be a single reinforced section. this value or this magical number 156 is came from BS 8110 3.444. This is the clause which mentioned this 156 value. This 156 value. Okay, now we know that this section can be exist as a singly reinforced section. Okay, for the requirement of steel or the reinforcement area, as we know that the tensile force is equal to 0.86 Fy As, we can calculate the total tensile force by using this equation. That M, or this is the maximum bending moment, is equal to T into Z. T means the tensile force, which can be calculated by using this equation, and the Z is lever arm. So we have to find the value of lever arm Z. There is an equation in BS 8110 3.4.4.4 3.4.4.4 in BS 8110 part 1 BS 8110 Z is equal to D into 0. Plus 0.5 plus 0.25 plus K over 0. This one is minus square root here. By solving this equation, as we know the value for D. We know the value for D, that is 475. We know the value for K. K is equal to this value 0.1108. K is equal to 0.1108. As we know all values, we can calculate Z. By using a calculator, we can get the value for Z. Z is equal to 475 into 0.5 plus square root 0.25 minus K over K means 0.1108 over 0.9 square root. The value is 406.7. So we can almost take it as 407 millimeters. This is the Z of the lever arm. This is the lever arm. This is the lever arm of the section. So by using these two equations, now we can find the required amount of steel here. This is the equation we have to use. M is equal to T into Z. It means in this section, this is the section, Z means lever arm. As we know, M means bending moment. Bending moment is equal to the tensile force into the distance between the compression and the tensile forces, that is lever arm. So Now we know bending moment as 115 to 10 to the power 6 Newton millimeters is equal to is equal to 0.87 Fy As, that is T or the tensile force, into Z. Z is equal to 407. It's 407. We can substitute these values. Fy is equal to 460, and we don't know the value for X As. You can find it by solving this. The value is equal to 115 to 10 to the power 6, 10 to the power 6 divided by 407 divided by 460 divided by 0.87. The value is 920.9. It is almost 921 square millimeters. We can take it by using two T25 bars, that is 981 square millimeters. So we can fulfill it. It means to this section it can withstand that amount of bending moment by using two T25 bars. Okay, now we can check the percentage of reinforcement, that is As over AC, that is 981 over 525 into 240. We can get the value using a calculator, that is 981 over 525 divided by 240, that is 0.007. Percent. It means it is over table 3.27 in BS 8110 part 1. We can get the minimum value, minimum reinforcement for 100 AS. 100 AS over AC is equal to 0.13. In our case, 100 AS over AC is equal to we have to multiply this value by 100. It means 0.7, that is greater than 0.13. It means we have satisfied the minimum value. Okay, it means now our section can withstand the bending moment which that section have to withstand. It means 150 kilonewton meters, this value, and our section values are also now okay. It means our effective depth is 50 millimeter lower than the total depth, and we use these data for our calculations. As a summary, because I selected this section, it means by using the given data, and I assume that this section is at the yield stage, then x over d, or the neutral axis over effective depth, is 0.5. To satisfy the single reinforced section, the k value must be 0.156. That is the maximum value to be a single reinforced section. To be 0.156, I found the effective depth. This is the minimum effective depth. We can use any value greater than this d. As a safety factor, I use 50 millimeters, and I use effective depth as 475 and total depth as 525. And then I calculate the k value. Then the value was 0.1108. As that one is lesser than this 0.156, this is okay for a single reinforced section according to the BS 8110 3.4.4.4. And after that, finding section sizes, I found the area needed for steel. For that, I needed to find the lever arm by using this equation, which is in the BS 8110 part 1 3.4.4.4. I found the lever arm, and then I substitute that value to this equation. This is the bending moment equation, and I found the area which is suitable for the section. And after that, I checked for the minimum reinforcement is satisfied or not, and I found that is satisfied. And that's all. Thank you.